All right, let's just jump right in. We are making more trash than we've ever made before, and that's a huge problem. But what if the answer isn't just about making less of it? What if we could actually scientifically transform all that trash into treasure? Well, today, that's exactly what we're going to dig into, the cutting-edge science of waste upcycling.
Look, there's no way around it. Every single day, cities all over the world are just grappling with these literal mountains of garbage. It's a massive environmental headache, right? It fills up our landfills, it threatens our ecosystems, and it's not great for our health. It can feel pretty overwhelming.
But what if we've been looking at this whole thing backwards? A lot of scientists are starting to completely reframe the problem. They're looking at our garbage, and they're not seeing an endpoint. They're seeing a rich, completely untapped raw material, just waiting to be turned into new, high-value stuff.
And that brings us to this key idea, waste upcycling. Now, this is not your everyday recycling, okay? We're not just talking about turning an aluminum can back into another aluminum can. This is about total transformation. It's about taking low-value waste and using some really advanced science to turn it into something way more valuable than it was to begin with. Think things like high-performance carbon materials or even clean, renewable energy.
So how in the world do we actually do that? Well, in a scientific world, there are two major approaches that are really leading the pack. You can kind of think of them as two powerful contenders, both in the race to solve our global trash problem. So let's break them down.
So first up, we've got what's called the thermochemical method. Really, it's just the power of controlled, incredibly intense heat. I want you to picture a super sophisticated high-tech furnace. It's not designed to just burn trash, but to scientifically cook it, breaking it down at a molecular level to create brand new materials.
And what's really fascinating here is that the research shows that not all furnaces are built the same. I mean, not even close. Turns out, a really simple change in the shape, just going from a rectangle to a cylinder with airflow from the bottom, makes a huge difference. That cylindrical shape gives you this perfect, symmetrical airflow that gets rid of any stagnant cold spots, which means you get a way more complete and efficient burn.
And the engineering just gets smarter from there. By creating this really clever alpha-shaped pathway for the hot gas to travel, scientists were able to crank up the temperature in a key part of the incinerator by a staggering 138%. And here's why that matters. This isn't just about getting things hot. It's about getting them hot in a very specific, targeted way. That kind of intense heat is what you need to completely break down even the toughest materials, which means you get more energy out and fewer nasty byproducts escaping.
Of course, this kind of brute force approach has its own set of problems. All that intense heat creates ash that wants to stick to the incinerator walls, and the bigger particles are 3 times as sticky, which can really gum up the whole system. Plus, you're in this constant battle against corrosion from harsh chemicals, and you absolutely need top-of-the-line control systems to catch any toxic emissions.
Okay, now for our second contender, which, honestly, could not be more different. This method is all about finesse. It's the power of biology. So instead of a furnace, imagine we're using tiny armies of microbes and fungi. It's kind of like putting a supercharged digestive system to work, just munching away on our trash for us.
And check this out, this is a brilliant example. A project called the Mushbox uses these modular bricks that are filled with mycelium, that's the root network of fungi. In some landfill trials, a single one of these units broke down over a ton of regular city waste in just a year. And what's even crazier is that it helps tackle some of our biggest problems, like breaking down microplastics and cleaning up that toxic liquid that seeps out of the landfills.
And another cool thing about biology is that it loves teamwork. This chart here shows what happens when you co-digest different kinds of organic waste together. So by mixing some food waste with regular waste sludge, scientists were able to boost the production of biomethane, which is a great renewable energy source, by a really solid 35%.
The versatility is just incredible. I mean, you have other biological methods like vermicomposting, which basically just puts earthworms to work. And the research shows that they can take nasty toxic sludge from something like the textile industry and turn it into safe, nutrient-rich compost that actually helps plants grow. It's amazing.
Okay, so we've got our two heavy hitters. On one side, you have the raw, fast, brute force of heat, and on the other, you have the slow, steady, super targeted work of biology. So, which one is better? Which approach comes out on top?
Well, let's put them head to head. The heat method, it's super fast, we're talking minutes to hours, and it can handle almost anything you throw at it, including plastics. Its big challenge is just managing the emissions and all that corrosion. The biology method, on the other hand, is a lot slower, days to months, and it's picky. It really only likes organic waste. But it gives you these totally different valuable products, like biogas and compost. Its main hurdle is just speeding things up.
So who's the winner? Well, this is where the story gets really interesting. The actual breakthrough here isn't about picking one over the other. The real winner is an alliance. It's about using both methods together to build a future that's truly circular and sustainable. Here's how that would work. First, you collect and sort all the waste. The non-organic stuff, the plastics and things like that, they go to the high-heat process to get turned into energy or valuable carbon. But the organic part, food scraps, yard trimmings, that goes to the biological process to become biogas and compost. You see, absolutely nothing gets wasted. And as the research synthesis puts it just perfectly, it's this dynamic interplay that really holds the key. You have the precision of heat working together with the effectiveness of biology. It's a powerful, complementary system that can actually tackle the entire waste stream.
So, if there's one thing to take away from all this, it's that the future of dealing with our trash isn't about finding one single magic bullet. It's about designing these really smart, integrated systems that can find value where, right now, we only see garbage. And that leaves us with one last, kind of provocative thought. Could the very trash we throw out today actually become the building blocks for a greener world tomorrow?